Hello students, today we will be dealing with another manifestation of surface tension, that is the excess pressure that occurs along a curved surface. After that we will be dealing with cohesion and adhesion, and then we will see how cohesion and adhesion and surface tension together leads to capillarity. Let's do the new topic, excess pressure. Now let us see what exactly is this excess pressure. Now consider a soap bubble of radius r. Consider a soap bubble. Let's see what is excess pressure within a soap bubble, and then we'll generalize it. Consider this is a soap bubble. If you have seen soap bubble, what is that? There is an air that is trapped within that bubble, and then there is a surface of the soap solution. So this is the surface of the soap solution. There is air inside, there is air outside, and then there is this layer. Now this layer is finite. It has a finite thickness, although not much appreciable from naked eyes, but this has a thickness. Now this thickness has two layers, right? One the outer surface, and then there will be a thickness of for 10 to 15 molecular layer, and then another surface that is within. So it's like this. Strictly speaking, the figure is like this. This is the soap solution that you see. This is the layer of soap. This is air outside, this is air inside. Now the question is, what is the excess pressure? Now there is an excess pressure that is present within from the outside. Now we know that pressure outside is atmospheric pressure. Now but the pressure that is inside, this is air, this is also air, but the pressure that is present inside is not atmospheric pressure. This is actually an extra pressure. This pressure is greater. If we name this P, so actually this pressure is greater than atmospheric pressure. How do we get that? So this is what we want to derive here. What we will do is that we cut this soap bubble through a cross section like this. If you cut it through a cross section, what is the surface that you have? After cutting, what I do is that I have cut it like this, and I am looking from here in this side. What is the surface that I will see? This is the surface that I will see. This is the surface that I see. This is the thickness, and as seen from this side, from the vertical, how I am looking, this cross section is like this. I have cut this. This is soap bubble. As seen from here, this is like a cross section. You will see a circle. Now as seen from this side, the view is like this. Now what we will do is that we try to balance all the forces, because the soap bubble that you see, it is in equilibrium. When it is in equilibrium, that means the net forces that will be acting on this will be 0. Okay. So now we try to balance the forces. Now let P be the pressure inside the bubble. We assume that the pressure inside is P, and PA is the pressure that is outside, which is normally the atmospheric pressure. Now the excess pressure is, what is excess pressure? This will be P minus PA, or if it is PATM, this is P minus PATM. Now considering the halves of the bubble, we write down all the forces that are acting on it. Now what are all the forces that are acting? Now one is the force that is acting on this portion by the other half. The other half that you had was like this, right? Now when you sliced it, this portion was attracted by this due to the surface tension of the liquid. Now if you consider this surface, now this is the surface. Now each element of this element is attracted by the element that is present for the other half. It is attracted because this liquid has a surface tension. Now what is that force? Now if this is of length dl, the force that will act is dF. If we apply, this is surface tension S into dl. Now we have taken here surface tension as T, so let's use the symbol T. So it's T into dl is the force that's acting on this element. What is the total force of surface tension? It will be throughout the circumference. So the force of surface tension T will be integral of dF, that is T into 2 pi r. This is the surface tension force that is acting on one half due to the other half. It's attracting, the other half is attracting this with this force. What are the other forces? Now other one is the outer force. Outer force from the outside is due to the atmospheric pressure. Now what will be the pressure of this? Now if you see, the pressure due to this and pressure due to this are somewhat cancelling. How? It will have a component in this direction as well as in this direction. This will have a component in this direction as well as in this direction. So what that means is, the pressure that we had, let's see it in this manner. This was the pressure, this component, the pressure due to this was this and this. These are the two components. Now if you see, the vertical components are actually cancelling out. right? So what is happening is that the vertical components have gone cancelled out, gone to 0, only the horizontal components are remaining. So when you apply for whole this, what you can do, you can add the components of the forces and then find out the total forces, or you can take the component of the area, because it's the component of the area, its projection, that will be acting on this. So the force that is acting due to this is actually outside forces, it will be pressure Pa into area. What is the projection of this hemispherical portion on this cross section? It will be simply 2 pi r square, right? Because the area of this surface, area of this whole surface will be 2 pi r square. So if you find out the component of this curved hemispherical curved portion on this cross section, it is simply this, or you can find out the forces component and then you will still get the same value. So it's Pa into 2 pi r square. Consider about the forces due to inside ones. Now inside ones, inside pressure was air, inside there was an air, so there will be a pressure from inside. So what is that pressure? The pressure from inside is, if you assume the value to be P, what we will have is, if I assume the value is P from inside. Now what is that pressure? What is the force due to this pressure? Again you will have the component thing, and the value of the pressure that you will get is P into 2 pi r square. If the pressure inside is P and the pressure outside is Pa. So now balancing this, what we will do is that we will balance all of these forces. So let's balance all these forces and let us see what is the equation that we are getting. So we balance it for static equilibrium. So what are the forces acting? The force acting from this side is atmospheric pressure, that is Pa into 2 pi r square, okay, and then there is a pressure on this part. Now we are considering this portion, this is surface tension into 2 pi r, and the pressure in this direction due to the inside of the liquid, that is P into 2 pi r square. Now if you balance these two, what you will get is Pa into 2 pi r square plus T into 2 pi r is equal to P into 2 pi r square. Now if you try to cancel out the things that we have, what you will have is the pressure into this, pressure into this. Now this is P. What you need to find out is P minus Pa. The value that you have to find out is P minus Pa. So we find out the value of the pressure. What you have is 2 pi r into T. This is balanced by P2 into pi r square. Okay, so this is actually pi r square. This is not 2 pi r square. The area of this is simply pi r square. 2 pi r square was the area of the hemispherical portion. We actually took the component, the projection of that on the slice that we have made. That is simply pi r square. So what you get is P minus Pa. This is T by, so 2T by R. So the expression that we have is P minus Pa is 2T by R. This is the change in the pressure. Okay, this is the change in the pressure that we get. Now why this is happening 4T by R? Why I have written here that the axis pressure is 4T by R? The reason is because this soap surface that we see, the soap bubble that we see, this actually has two surfaces. So if we assume the pressure, this was Pa, so this is actually the pressure in this liquid. Let me make a figure for you like this, an exaggerated view, and then it will be clear. So if you assume that the pressure here is Pa and the pressure here is P, that is the inside pressure, you will get the pressure difference P minus Pa as 2T by R. Now if you have to find out what is the pressure difference from the atmosphere, the outside, now what will happen, you will have to again apply for this curved surface. Now when you again apply the curved surface for this, now the radius of this, we assume that the radius for both of this is R, because that thickness is very small. Okay, so when you will apply for this, you will again have 2T by R. So P minus, if you take this as the outer pressure, so what you will have is 2T by R plus 2T by R. You can write it like this. P minus Pa is 2T by R, this you know. When you apply for PATM minus Pa, what you will have is PATM minus Pa is again 2T by R. what you need to find is P minus P ATM, because if you need to find the outer minus inner, we put this, you will get 4T by R. So this is the access pressure between inside and the outside. Had there been only one surface, the pressure would be 2T by R. When there will be one surface? So the example that we have for one surface is when you simply have a water bubble. What happens in water bubble? You have a water bubble like this. The water is there throughout filled with. Now this has only one surface, the outside surface, nothing else. Inside totally there is a liquid, there is only one surface that is formed between the liquid and the air. So when I say surface, the surface means those surfaces where the surface is changing its nature, means whether when the two surfaces are either solid liquid, you have to consider those number of surfaces. Now when everything is liquid, then there is only one surface, that is the outside surface, inside is the bulk. So in soap what happens? There is one surface this, there is another surface this. In a water bubble you only have one surface. So we have got this value. Now let us see this question. We have two soap bubbles, each with a radius r. They coalesce in vacuum under isothermal condition to form a bigger bubble of radius r, then r is equal to. What does it mean when you say isothermal condition? That means the energy is conserved. You have to find what will be the radius of the coalesced ball. Now these two coalesce to form a larger ball. These are smaller bubbles, small radius is r, this is of capital radius capital R. Now what is the surface energy of this? You only have to balance the energy conservation because it is given as isothermal. So the energy of this will be, the surface energy we know is the surface tension T into the area created. Now what is the area that is of this, created of this, is tension T into 4 pi r square. Now since this is a soap bubble, this is important, since this is a soap bubble, the area that you have, the area created are actually twice of 2 pi r square. If you assume this is also r and this is also r, why assuming the inner radius and outer r? Because the thickness is very small. Although I have exaggerated this view here, this is actually same. So you have two surfaces, one is this surface is going from air to liquid, and then this surface going from liquid to air. So always I have to see a surface where it is changing from liquid to air or air to liquid, that makes the surface. So you will have this, and this is twice of this, because we have two soap bubbles. So this is total surface energy initial. What will be the surface energy final? It will be simply 2 into T into 4 pi capital R square. Now if you equate these two, what we have is, so you will have 16 pi R square into T is equal to 8 pi R square capital R square into T. So 8 pi into T will cancel, pi T, and this will make this 2. So capital R is actually 2 to the power half into R. So if you look at the answer, correct answer is this. Okay, let's move to the new topic, cohesion and adhesion. Now what is this cohesion and adhesion? Now molecules in the liquid state experience strong intermolecular attractive forces. Now when those forces are between like molecules, they are referred to as cohesive forces. Now when the attractive forces are between unlike molecules, they are called adhesive forces. Now consider a surface here like this. This is a liquid. Now if you consider a molecule of the liquid here, if you consider a molecule of the liquid, consider this region. In this region I am considering a molecule of the liquid. This molecule if you consider, now this is attracted by the liquid molecules, all of the liquid molecules that are present throughout from this region to this region. So the net force will be somewhere like this. This is the forces due to the liquid on the liquid molecule. This kind of force is called cohesive forces because it is between liquid and liquid. So this is the cohesive forces. Now this molecule will also be attracted by the solid capillary surface that you see. Now this solid capillary surface will give you a force that is called adhesive forces. adhesive force will act in this direction. This solid, that flask or the capillary tube, whatever is, the molecules of that will attract this liquid. So what there is one more force. The one more force that is remaining is the weight of this liquid, that is its weight mg. So these are all the forces that are acting on any molecule that you consider which is present on the surface touching the container. So that means if you try to balance down these forces applying the Newton's law, what we'll have is, this is adhesive forces, this is Fc resolved into this. Now since this is exactly in the middle, it's Fc sin 45, Fc cos 45. So then we balance the forces. What are the net forces? We have seen here the forces acting are the weight mg of the molecule exactly acting vertically downwards. The force of adhesion was acting along OA. You have seen what OA direction is, it's outward from the surface to out. Cohesion acting along OC. If I draw the figure again here, you had this point was OA, this was A. Cohesion was OC like this, acting along this, mg was acting like this. Then you resolve this into two components. This was Fc cos 45, this was Fc sin 45, this was Fa. Okay. Now, so what are the horizontal forces? Net horizontal force is actually Fa minus Fc cos 45. You can see the direction of these two are opposite. And the net forces acting downward is the Fc sin 45 plus your weight mg. Now you see, when these forces balance, this gives you the shape of the liquid. How they give you the shape of the liquid? So suppose if the net forces balance on the horizontal, what will happen? If these two forces component balance, then only this vertical component remains. When this will happen, the surface of the liquid will be like this, like a horizontal, because the net force on any liquid on the surface, it must act perpendicular to the surface. Net force on this must act perpendicular at any point of time, because if there will be a component in this direction, suppose the net force is like this, what that means is that it will have a component in this direction as well as a component in this direction. Now this tangential component will set this in motion, the fluid in motion. So that means what? It will violate that the fluid is at rest. So the net force must always be vertical. So when these two forces balance, it's simply like this. So if the net force is acting like this, the surface of the liquid must be perpendicular to this, because net force always acts perpendicular to the fluid. So the surface of the liquid will be like this. What will happen when this is there, these two don't balance? Then what can happen? One thing can happen, that the net force is in this direction. So if the net force is in this direction and then you have downward force in this direction, the resultant of these two will be in this direction. Okay. Now it is easy to see that if the net force is in this direction, what will be the surface? Surface must be like this, because the force has to be perpendicular to it. So if I highlight this angle, what you have is, since the angle has to be 90, because the net force will always be perpendicular to surface, surface must bend in this direction. What will happen when you will have a net force in this direction and this is a downward component, the net force is like this. So the liquid surface must become like this, because when liquid forces will become like this, now this angle is becoming 90, otherwise it is not possible. So by looking at the cohesion and adhesion forces, you can tell what kind of surface it is going to have, whether it will be concave convex upward or it will be concave upward. Now this adhesion of water molecules to the walls, now you see, you have seen how it is, liquid is gaining its shape. Now we will see what is the effect of surface tension. Now it has a tendency to make the surface like this. Now this, what it will do is that surface tension pulls these whole things upward. Because of that pulling and the surface tension holding the surface together, because surface tension, what it does is like it makes the surface like a stretched sheet. So it brings the whole liquid column above. The surface tension on the surface brings the whole thing above, because it holds the surface together, and then this cohesion and adhesion, it pulls it up. You have seen it. Or it can pull it down. When the cohesion and adhesion has net force going down, it's pulling it down. So when it is pulling it down, the surface is concave, convex up, and it's pulled down. So the liquid will be like this. So if you try to put it like this, means if you have a liquid like this, if you have a capillary like this, and if this condition happens, the liquid is up to this level, you will have liquid in this container like this, up to this height. that has been dipped down. It will be below the normal level, and in this case the liquid will rise up. So means if you have it like this, liquid level is up to this, you will have this surface. Sorry, this surface means it's downward that we have seen here. So the surface tension acts to hold the surface intact. So instead of just the edges moving upward, the whole liquid surface is dragged, because the cohesion and adhesion will try to drag the surface that is in contact with the flask or the capillary. It will try to drag only those, but the surface tension, what it does, it holds the whole surface together, so it pulls up the whole thing. So we have seen how this is acting. Now capillary rise method. Now what is contact angle? Now what is contact angle? Contact angle is the angle that is acting between the surfaces that you have seen, the surface when it becomes concave or convex. Draw the tangent to this surface first, the tangent to solid surface, going towards liquid. So this solid surface, and then you have to draw the tangent to liquid surface away from the tangent, then you have to draw from the tangent to liquid surface away from the solid, so it will be here. Now the angle between these two tangents is called the contact angle. These two tangents that I have drawn to the solid surface, you always draw towards the liquid, so this will always be like this. But what will happen when the surface will be in this manner? Then the tangent to this surface will be like this, because you have to draw it from away from the solid. So this angle then will be the contact angle. So in this situation the contact angle is 90. Okay. Now here we have to find out what will be the height of the liquid that goes up. We have seen that it will be concave up or convex, or it could be flat. Flat when theta is 90, this contact angle is 90. What will be the height of the liquid that goes up? See how to find out the height. Now if you consider this liquid, now the pressure at this point will be atmospheric pressure, so will be the pressure at this level, right? Because they are at the same level, P atm. Now this is open to the atmosphere, so this is also P atm. Okay. So what is the pressure at this point? This is atmospheric pressure, this is atmospheric pressure. So the question can come in, if both are the same pressure, how is the liquid has gone up? There must be a pressure difference so that liquid can rise up. There is no pressure difference. So the answer is it has gone up due to surface tension. Now the surface tension that is acting in this surface, in this, if you consider this, surface tension on this portion is acting in the upward direction like this, on all of the elements of this the circular surface. So if the surface tension is T, surface tension force will be T into 2 pi r, where r is the radius of this capillary, because this is circular surface. Now this force must be balanced by the weight of the liquid that has gone up. Surface tension force will be balanced by the weight of the liquid downward. Weight of the liquid will be its volume of the liquid into density of the liquid into G. Volume of the liquid will be area of cross section of the liquid, that will be pi r square. Area of crossing, then the height of the liquid is h into rho into G. Now if you balance these two, you can see the pi get cancelled out, r will get cancelled out with this. So height h is 2t by height is, okay, it's 2t by rho G h. This is the height of the liquid that has gone up. If you write the what is the surface tension sigma, if you denote this by sigma, you will see that this T is actually rho G h into, okay, this was r, sorry, this was r, so rho G h r by 2. So this is what we have written here, where G is as usual the same value. So we have seen this is when the liquid is flat. Let us see what happens when the liquid is not flat. Liquid is like this. What is happening? What is the difference that has happened? Now if you look at this surface closely, surface is like this. So the surface tension force that will be acting will be in this direction. On an element that you consider this element seen in this manner. On this element, the surface tension forces are acting in this direction, because the surface is going in this manner. surface is going in this manner, so the surface tension force is acting like this. So if this angle is theta, which is your contact angle that you know, why? Because this is the tangent to the solid going inside and the tangent to the liquid going away from the solid is this. So if this is theta, this is also theta. So this theta is none angle other than the contact angle. Now what will happen when you apply the same surface tension thing here? Because the pressure at this point is PATM, so is the pressure at this point. Now the pressure at this surface will also be PATM. So how is that it's going up? It's going up due to surface tension. Now if surface tension acting on the element dl is, we use the symbol sigma, it's sigma into dl. But what will happen if you resolve the component in this direction and in this direction? What you see here is that, okay, now these components that you find at all of the elements throughout the section the horizontal components will get cancelled out. What remains is these vertical components throughout the section that will drag it up. So the only forces that are dragging it up is sigma dl cos theta, not the sin theta component. Sin theta is getting cancelled out. So when you net force, when you find out the net force due to surface tension, its integral of this will be sigma cos theta is a constant, integration of dl will be 2 pi r throughout the circumference. So if you balance this again, what you will have is sigma into cos theta into 2 pi r is the weight of this column. Again the weight of this column will be, we know it's volume density into g. Volume is the area of cross section, that is pi r square, into the height of the liquid is h. Now if you see here, this surface is curved. So what we are doing is that we are neglecting this portion of the fluid. And then we are taking that it has gone to height h. We are assuming, because that volume will actually be very small, so into rho g. So if you equate this, you will get this. Simply this cos theta comes in. This remaining part was present there also when it was flat. This cos theta factor has come in. Now what will happen if you try to consider this portion? You will have to find the volume of this. Now what will be the volume of this shaded surface? You can find out in this manner. Find out the total volume of this. So if this is r, this will also be radius r, right? This is radius r. What will be the volume of this cylindrical portion? Now this cylindrical portion volume will be pi r square into h is again r, because this is like this portion I am considering. Volume of this whole thing, this is like a circular cross section, and then I will subtract from this the volume of this hemisphere. If from this cylinder I subtract this volume, I will get this shaded portion. Okay, so I am subtracting this. So volume of the cylinder will be pi r square into r. It's pi r square h, so we have done this, minus volume of this. Volume of the hemisphere is 2 by 3 pi r cube. So what you get is pi r cube minus 2 by 3 pi r cube, that is 1 by 3 pi r cube. So if you consider this volume, what will the change that will come in? You will have this weight plus this weight, plus you will have 1 by 3 pi r cube is the volume into rho into g. So similarly the value will change a bit. You can find out from here. Okay, let's see question. Water rises to height of 2 cm in a capillary. Okay, if the tube is tilted 60 degree from the vertical. Now means if you tilt it like this from 60 degree from the vertical, so this angle is 60. This is liquid. Water will rise in the tube to a length. Now what is the height to which this liquid will go up? It's given is 2 cm. So if it's 2 cm here, so in this situation when you tilt it, still the height that it should go should be 2 cm. So if this is 2 cm, the liquid that will go into this, it must also be up to this height, 2 cm, because the pressure at the same depth is same. So that means the height is the perpendicular height. So even when it's tilted like this, the liquid must fill up to this height in this. So you have to find out this, so it's very easy. So this is given when you tilt it like this angle is 60. This was given as 2 centimeter. We have to find out water will rise in the tube. What will be this length? Because now the tube is tilted like this. What is the length of the liquid? So it's simply this. If we apply this, cos 60, cos theta will be 2 centimeter by, if I denote this by x, this is x. X will be 2 by cos 60. Cos 60 we know is root 3 by 2. Sorry, cos 60 is 1 by 2. So what you get is 4 centimeter. So the correct answer here is 4 centimeter. So students, we have seen cohesion and adhesion and how it combines with surface tension leading to capillarity. In the next topic, we are going to deal with some of the IIT-JEE questions. So stay tuned with Ask IITians for the next topic.